Hello, I'm Luke, and welcome to our paper, Deep Spectral Methods, a surprisingly strong baseline for unsupervised semantic segmentation and localization. This is work done with Christian Ruprecht, Ireliana, and Andrea Vidaldi in the VGG group at Oxford University. This paper is about combining deep self-supervised learning with classical graph theoretic methods to tackle a variety of computer vision tasks without supervision. I would say that if you're only going to take one thing from this presentation, I hope it is the idea that the intersection of modern and classical methods is a powerful combination, especially in low data regimes. The catalyst for our work is that over the past 2 years, the field of computer vision has seen the emergence of vision transformers, and numerous works have shown that these models produce better localized features than traditional convolutional network. In our work, we describe an approach for extracting well-localized semantic information from these transformers using graph theoretic methods. Differently from most modern approaches to segmentation, we take inspiration from traditional methods from the early 2000s, which aimed to segment images with non-learning based algorithms that operated on pixel intensities. These methods consider images as graphs of pixels and apply classical ideas from spectral graph theory, which we'll dive into next. Formally, consider a real function x defined on a weighted graph G with edge weights W. We can quantify the smoothness of x with respect to G by measuring how much x varies, weighted by W. This quantity is a quadratic form, known as the Laplacian of G, which can be calculated efficiently as D minus W, where D is a diagonal matrix containing the row-wise sums of W. At a high level, you can think of the Laplacian as a functional, which measures the smoothness of functions on our graph. The field of spectral graph theory aims to understand properties of graphs by examining the eigenvalues and eigenvectors of graph Laplacians. These are natural objects to study because, as expressed by the Courant-Fisher formula, the eigenvectors are in some sense the smoothest possible orthogonal basis for functions on G. The first eigenvector is particularly important, and we will use it to perform single object segmentation. When using the ideas for image segmentation, the nodes of our graph correspond to image pixels or patches, and the edge weights correspond to pixel or patch affinities. There's been a tremendous amount of research on this topic over the past 20 years, mostly going under the name graph cuts and spectral matting. A large portion of this research was dedicated to the choice of the affinity matrix W, for which many variants have been proposed. Our method fuses traditional pixel-based affinities with semantic affinities obtained from a self-supervised vision transformer. Specifically, we extract features f from the last attention block of a self-supervised transformer, such as Dino or Mocha v3. We then calculate the eigenvectors of the corresponding Laplacian, which can be thought of as soft image segments, and we use them for downstream tasks. Here, you can see an illustration of this process. At the top, we extract features and calculate the Laplacian. Then, for the task of object localization, we simply take the first eigensegment, threshold it, and take its largest connected component. For the task of semantic segmentation, we cluster our eigensegments within each image, extract features for each of the clustered segments, and then cluster these features across the entire dataset. Our paper contains all the details, but overall we want to emphasize that this framework is incredibly simple, and despite this simplicity, we perform well across a wide range of datasets. Here, we show some qualitative examples of our extracted eigensegments. Next, we show examples of object localization, of single object segmentation, and finally of semantic segmentation. In addition, our framework can also be used for automatic semantic image matting. Quantitatively, we perform favorably to past work. Here, for example, you can see that our simple spectral method is significantly better at extracting localized regions than the standard method from the Dino paper, which is shown here as Dino CLS. Finally, it's important to mention our work's limitations. Our model is highly semantic, meaning that it often groups together different instances of the same semantic category. Future work could help address these limitations, as well as extend our method to other tasks, such as semi-supervised segmentation and domain-adaptive segmentation. All of our code is online. Thank you so much for listening, and I hope to see you at a poster session.